Welcome to this video on digital electronics. Can you recollect some of the digital systems that you can remember? The computer, laptop, yes, and then look around you. The digital clock, digital watch, television, radio, digital music system. Walk around your house. The washing machine, refrigerator, microwave oven all use some form of digital systems and lots more of consumer electronics. Step out of your house, the traffic signal, the GPS system, communication system, the digital display boards, the radar system, medical instruments, many such digital systems that are being used. So, in this video we will be looking into an overview of digital electronics, what digital systems are and why we need to use digital systems. Before looking into what a digital system is, we will try to understand the difference between analog and digital signals. First, a signal, it is a variation of quantity in time. For example, temperature. The temperature of a room varies continuously with respect to time. At any given instant, the temperature of a room has a specific value. So, this variation of quantity with respect to time is called the signal. Examples are temperature, pressure, speech, video, and if using a transducer any of these signals is converted to an electrical quantity, then it is called an electrical signal. So, an analog signal is basically a signal that varies continuously, that is it can take any value at any instant of time between a predefined range. For example, the temperature of room could vary from 20 to 45 degree for a hot country. At any given instant of time, the temperature could take any of these values, or the voltage level. If it could vary between 0 to 5 volts, then at any given instant of time, the voltage can assume or take up any of these values. So, analog signal is a signal that varies continuously with respect to time and it can take any value within a specified range. Now, if you are going to observe the temperature of a room, then you will be noting it down at specific time intervals, say at half an hour interval or 1 hour interval. So, this discretization in time produces a discrete time signal, and at each instant of time the temperature that is monitored can take up any value in the predefined range, say what we have discussed 20 to 45 degrees, or a voltage level could be between 0 to 5 volts at any given instant of time. So, here the time domain is discretized whereas the amplitude is continuous. So, the temperature is noted at discrete time instance, but the amplitude or the value of temperature can take up any of the values as discrete time signal. Now, if we want to discretize the amplitude also, have discrete amplitude, that could be done by quantization. That is, quantization levels are fixed in the amplitude for this given range of values that can be taken up, and only the specific quantized levels or values at an instant are noted. So, now the signal is discretized in amplitude also. So, by sampling we can discretize a signal in the time domain, and by quantization we can discretize it in the amplitude domain. So, discrete amplitude and discrete time signal is called a digital signal. Let me repeat, an analog signal is one that varies continuously with respect to time and with amplitude. So, at any given instant of time any value of amplitude can be taken up, whereas a digital signal is one that is discrete in the time domain and discrete in amplitude domain also. Analog signal can be converted to a digital signal by sampling and quantization. So, digital system basically deals with discrete signals. It stores, processes and communicates information in the digital form. But in the real world all signals are analog in nature. So, these signals have to be converted to digital so that a digital system can process it. So, the block diagram here shows such a system. The analog input, it is converted into the electrical form using a transducer, and then this signal is conditioned and then converted to the digital form using ADC or analog to digital converter. This digital signal is given as an input to the digital system which processes the signal, and the signal can be either stored or used in the digital form itself or converted into analog form using DAC, that is digital to analog converters. And this output signal is conditioned such as smoothing filters or amplifying the signal before feeding it to a speaker and so on, and the analog output is used. So, an analog signal is converted to digital signal using ADC and the digital system processes it, and then it is converted back to analog signal using DAC or digital to analog converters. And the digital electronics course that we are going to deal with will be considering the digital system alone, where the signal is operated upon in the digital form. Now, I said all real world signals are analog in nature. Then why do we need to convert it to digital form, process it and then reconvert it into analog form again? Why not process the signal in the analog form itself? Here are the reasons for it. Digital signals are easy to process, store, reproduce and transmit. That is, processing of digital signals has gone to such an extent that we have digital signal processors which can perform intensive and complicated operations. And then to store analog signal, analog values are stored in capacitors which discharge, therefore the values are unreliable. Whereas in a digital system, data can be stored for any long period, and also compact storage is possible, that is, large volumes of information can be stored in small areas. And digital systems are more reliable compared to analog systems. Digital systems are less affected by noise, that is, the effect of noise on digital systems which take up a value of 0 or 1 is less compared to that of an analog system. Then accuracy is higher in a digital system. That is, if more accuracy is required in a digital system, all that we need to do is increase the number of quantization levels, which would in fact require additional hardware. So, for higher accuracy, the number of quantization levels is to be made more. In analog systems also the accuracy can be improved, but here the precision measurement system precision should be improved, which becomes costlier compared to a digital system. And then overall a digital system is more cost effective compared to an analog system. And the ease of portability. A digital system, if it is designed for a particular application, it can be easily changed by changing the program. So, there is ease of portability, and also digital systems are easier to design. These are some examples, one of a pure analog electronic system, another is a combination of analog and digital systems. And first is a public address system, which is an analog electronic system. Here the speaker's voice is converted to electrical form using a microphone, and then the signal is amplified by an amplifier and then fed to a speaker which converts it into sound which reaches a larger audience and covers greater distances. The second example is that of a CD player, which is a combination of digital and analog electronic system. Here in a CD drive, the music is or data has already been written onto the drive and it is stored in the digital form, and a digital reader such as a laser can be used to read the digital data, and this data is converted to analog form using DAC, that is digital to analog converters, and this analog signal is amplified and then fed to a speaker from which the music or the output speech can be heard. The digital systems have two-state number system called binary number system, and the two states that are possible are high and low, represented by logic 1 and logic 0, and each binary digit is called a bit. So, bit 1, bit 0. The two diagrams show a positive going pulse and a negative going pulse. So, in the positive going pulse, the pulse goes to the high level, remains there for a certain duration and then comes back to a low level. So, it is a positive pulse. So, in a positive going pulse, the transition from low to high level is called the rising edge, and the transition from high to low is called the falling edge. The x axis considering the time and the y axis the amplitude. So, the rising edge arrives at an earlier time duration compared to the falling edge. For example, if we mark along the x axis the rising edge at 2 millisecond and the falling edge at 4 millisecond. So, the rising edge occurs earlier in time with respect to the falling edge. Therefore, the rising edge is called the leading edge and the falling edge is called the trailing edge because it comes later. So, in a positive going pulse, the low to high transition is called the rising or leading edge, and the high to low transition is called the falling or trailing edge. Similarly, in a negative going pulse, high to low is the falling or leading edge, and low to high is the rising or trailing edge. So, we are talking of logic 1, 0, high, low, but how will a computer understand these levels, the binary levels? So, we use voltage or current levels to represent the 1 and 0, and they are called logic levels. In a considering voltage logic level, positive logic, a 0 is represented by a lower voltage level and 1 by a higher voltage level. For example, 0 volt represents logic 0 and plus 5 volt represents logic 1, or it could be minus 5 volt represents logic 0 and 0 volt represents logic 1. And in the negative logic, 0 volt is represented by the higher voltage level and logic 1 is represented by the lower voltage level. Example, plus 5 volt for 0 and 0 volt for 1. The diagram shows the positive logic voltage levels. So, logic 0 is when the voltage lies in a value between VL minimum and VL maximum, that is lower voltage minimum and lower voltage maximum value. And when the voltage level is between VH minimum and VH maximum, it is logic 1 or high. Any value between VL maximum and VH minimum is invalid or unacceptable. The example that is shown is for a TTL transistor. When the voltage is between 0 volts and 0.8 volt, it is logic 0, and a voltage between 2 volts to 5 volts is logic 1, and any value between 0.8 volt to 2 volt is invalid. So, for example, a 0.5 volt input to a transistor would be considered as logic 0, and a 3 or 3.5 volt to the transistor would be considered as high voltage level. So, in this video we have seen what a digital system is and why we need to use digital systems when real world signals are all analog in nature. Why do we need to convert signals to digital and process it over there? We have seen the advantages of using digital systems. These are the references. Thank you.